The graph of a function f of two variables is the collection of all triples xy f of xy where xy belongs to the domain of f. So you're looking at all the points, all the triples of this form in the 3 space where the first two coordinates, they vary over the domain of the function. In fact, one can think of the function in this way, that a function is a collection of ordered triples where the third coordinate is the value of the function at the input xy. So typically, if you can imagine that you have the domain of a function of two variables, and then for each xy in the domain, you calculate z equal to f of xy, and then you plot the point xyz in the 3 space, and so that would be a point on the graph of the function. So typically the graph of a function of two variables is a surface in the 3 space. If I have a function of 3 variables, then its graph would be the collection of all quadruple x, y, z, comma f of x, y, z, where x, y, z belongs to the domain of the function. If I have a function of n variables, then the graph would be the collection of all n plus 1 tuples, where the first n coordinates, they belong to the domain of the function. Here is an example. So if I have the function f of xy is equal to x squared plus y squared, where the domain is given by this inequality. So notice that what's the domain here? It says x squared plus y squared is less than 4. Now recall that x squared plus y squared is basically the square of the distance from the origin to the point. So if I look at the origin 0, 0, and if I look at the point xy, then the distance from 0, 0 to xy, that is root of x squared plus y squared. So this inequality tells me that the distance between xy and 0 and the origin is less than 2. So this inequality is giving us the set of all points in the disk of radius 2 centered at the origin. So the domain here is this disk of radius 2 centered at the origin. And the graph of this function, well, I'm going to denote f of xy by z. So we're looking at the graph of this equation, z is equal to x squared plus y squared, and from what we have learned in the section on quadric surfaces, we know that this is a paraboloid that opens upward, and so we get this paraboloid here, and so we're not getting the entire paraboloid here. We are only getting the part of the paraboloid that is right above this disk of radius 2. So, and notice that basically the paraboloid is we're going all the way up to z equals to 4. So when z is 4, this is the trace. This is the trace in the plane z is equal to 4. Is this circle of radius 2. So we are getting the paraboloid, a part of the paraboloid from z equal to 0 up to z equal to 4 here. Okay, so let's look at the next one. So if I have f of xy is ax plus by plus c, then what's the graph of f? Well, labeling f of xy by z, then we get z is equal to ax plus by plus c, which is equal to ax plus, which can be rewritten as ax plus by minus z is equal to minus c. So we see that the graph of this function would be a plane which is perpendicular to the vector a, b, comma, b, comma, minus 1. If I take a, b to be 2 and 3 and c to be 5, I guess I'm taking c to be negative 5, then the graph of f would be the same as the graph of this equation here, and in that case you see that we get a plane which is perpendicular to the vector 2, 3, negative 1. Okay, if I look at the function f of xy is equal to root of 9 minus x squared minus y squared, what is the graph of this function? Well, again, set z to f of xy, then we get this equation. If I square both sides, then I get z squared is 9 minus x squared minus y squared. And then if I rewrite this as x squared plus y squared plus z squared is equal to 9, then we see that we get this sphere of radius 3 centered at the origin. But we're not going to get the entire sphere because z is positive root of this quantity. So z is non-negative. So we are getting the upper half of the sphere of radius 3 centered at the origin. So here the graph of this function is the upper half of the sphere of radius 3 centered at the origin. One more example on this. So let's say z is at the function f of xy, which is equal to e to the negative x squared plus y squared. Now what's the graph of that? Well, first of all, let's look at the trace in the yz plane. So the trace in the yz plane, so I'm going to take x to be 0, so we get z is equal to e to the negative y squared, and the graph of this equation in the yz plane is a nice symmetric bell-shaped curve. Now let's look at the traces in the planes z equals to k. So if z is k, then we get this guy is equal to k, and obviously k has to be positive because the exponential function here is always positive. Now if I take natural log on both sides, so I get ln of k is equal to negative x squared plus y squared. So x squared plus y squared is equal to negative ln of k. Now since x squared plus y squared is non-negative, we see that we need to pick k to be less than 1, because if k is bigger than 1, then ln of k would be positive, and then we get a negative number here. So when k is, we already know k is positive, and when k is less than or equal to 1, then we know that ln of k would be non-positive, and then with the negative it will be non-negative, and then this equation will make sense. So k has to be between 0 and 1, and then we see that this equation is actually a circle of radius given by negative ln k, and it is centered at 0, 0. So you get at this height k, you get a circle of radius given by negative ln of k as the trace. So basically you see that what kind of surface you're getting. It's going to be a nice symmetric bell-shaped surface, kind of like a really nice symmetric mountain. Okay, so that's the graph of this function. Okay, so in the next video I will show you how to sketch the graphs of functions of two variables in the using Maple. See you then.